Dr. Sirisha, working as Associate Professor in the Institute of Aeronautical Engineering College. Today we are going to discuss about expression trees and threaded binary trees. Let me introduce you expression trees. Expression tree is nothing but a binary tree in which the internal nodes are the operators and leaf nodes or the external nodes are the operands. Have a look at this picture. I've taken an expression, a binary expression. You can see 4 plus 5 multiplied by 8 by 2. Here you can see that there are two terms in this one. The first term will be 4 plus 5, which will be evaluated first. The second term, which will be evaluated, is 8 divided by 2. The result, the third step will be the multiplication of the results of the first as well as the second steps. So this process can be pictorially represented using binary trees. So let me show you this here. So the left subtree over here depicts the first operation which I have mentioned over here, which is 4 addition 5, right? And the second sub expression is depicted with this picture, which is the right mode of multiplication, which is 8 divided by 2. As a whole, multiplication is at the root node, which shows you the basic multiplication of the first as well as the second expression, which is the result of the given expression, the final result of the given expression. With this, you can understand that expression trees are binary trees and they are placed, the operands and operators are placed in infix order. If you write the infix expression of the given binary tree, you are going to get the given expression which you are supposed to evaluate. So what is the infix expression of the given binary tree? So infix expressions goes with the funda of left node followed by the root followed by the right node, right? So first of all, I'm going to start with the root. As we all know that when we work with nonlinear data structures, which is tree, we have only one node's address in our hands, which is the address of the root. That is the address of the star, right? So I'm going to travel in leftward direction towards the left subtree. We're going to encounter less as the root of the left subtree of the multiplication operator, which is addition. As it is having a left operator, I'm going to run in this direction, and 4 as it is a leaf node, I cannot further move in left or right direction. So 4 is the first character. So once 4 is read, as it is an infix expression, so once left is done, I have to print the root. The root of 4 is addition. Once the root is done, I'm going to travel towards the right child of addition, which is 5. So as 5 is not having either left or right child, I'm going to print 5, right? So as this is the first expression, I'm going to place it within a bracket, specifying that it is a sub expression of a given expression, main expression. Okay, so with this, we can say that the whole left subtree of the given root is over. So once it is done, the left subtree, parsing to the left subtree is done, I can go with printing of the root, right? Once it is done, I'm going to travel in the right direction towards the head of the right subtree. And the head of the right subtree is division. Okay, is there any left or right subtrees of this division operation? Yes, I do have a left subtree. So I'm going to travel in the left direction where I'm going to encounter 8. Is 8 having any left node? No. As it is not having any left node, I'm going to straight away go with 8, that is the root. As it is not even having any right child, so parsing towards the left direction or the left subtree of division is done. Once it is done, I'm going to go with the root, which is slash, right? So once the slash is done, I'm going to go in the direction of right side of my slash, which is towards 2. I'm going to encounter a operand 2. As 2 is not having any left operator, I'm going to go with the root, which is 2. As it is not even having any right operator, so with this I can say that I have completed passing towards the right subtree of the star operator, right? That is a multiplication operator. As 8 by 2 acts as a sub-expression, I'm going to put it in the brackets, right? So with this, you can see that I got the infix expression of the given expression, right? So just by following the in order traversal, just by writing the in order traversal, you can get the infix expression of any expression tree, right? So why we use expression trees? Expression trees can be used are going to help you to evaluate expressions, to store the data and evaluate them more and more easily, right? So let's have a look at how to construct an expression tree from a given infix expression. In the previous first slide, I have shown you how to write or to how to extract the infix expression from an expression tree. Now I'll tell you construct how to construct a binary tree or an expression binary tree for a given infix expression. Have a look at this expression. You can see that this given infix expression is having nested or he's having nested brackets also. So a plus b is an operator which is a sub expression which is embedded within the main. Okay, so this we are going to convert this whole expression, the given expression, we are going to convert it into an expression tree. For this purpose, I need 2 stacks. One stack I'll be using to store the characters. The other stack I'll be using to store the nodes of the binary tree, which are actually going to get converted into the nodes of the binary tree, the expression binary tree. I'm going to use the node stack. Just to store the characters, I'm going to use the character stack. That is the first stack. Please keep one thing in mind. Here, guys, remember one thing. The first and foremost point is open brackets and operators. Both are going to go with the character stack. Whenever open bracket or any operator is encountered, let me make it very clear, any operator is encountered, you are going to push it into the character stack. There is a sub condition over there. When we insert operators into the stack, be sure that if there is already a character existing on the top of the stack, it should have a lesser priority when compared to the token in your hands, right? So very simple funda, an operator with higher priority, with higher priority cannot be inserted or cannot be pushed into the character stack, right? So for that, what you have to do? Simple, you have to pop it, send it to node stack, and then push. Okay, I'll give you a clear-cut description of the same. You need not worry about that. After the first rule, which implies for brackets as well as operators, the second is what if you encounter an operand? We know that in an expression tree, operands always settle down as leaf nodes or external nodes, right? So there is nothing to work on them. So straight away send them to nodes, right? So these are the two rules which you need to keep in your mind before starting this process. Let's start this process, my dears. So first of all, we have an opening bracket. So if you divide the given expression, understand guys, open bracket, the list of tokens are like this. A plus B, closed bracket, star C minus E star F, closed bracket. This is the list of tokens which are there in my hands. When we write a program for this one, we are going to read the infix expression as a string, and we are going to read character by character, right? For that sake, I'm explaining you in this way. So the first character that is in our hands is an open bracket. As I said, if we encounter an open bracket, kindly insert it into the stack. Which stack? Character stack. Please keep that in mind. Character stack. Once you insert it, what is the next character? The next character is another opening bracket, right? So push it into the character stack. What is the next character? The next character is an operand. The token, let me change my words as tokens. Let me use that word tokens, because character, you may get confused with the character stack and the term character. Okay. So what is the next token? A. A is the next token. So as it is an operand, push it into the node stack. Right? This is the current position. What is the next one? Is addition, which is an operator. Push it on the head of the character stack. So the top of the stack is pointing to plus. And here in the second one, the top of the stack is pointing to A. Right? Once addition operation is done, the next token is B. As B is an operand, simply push it into the node stack. Now here it is B is on top and addition is on top. So addition is on top of your character stack, whereas B is on top of your node stack. Very good. What next? The next character that you are going to, or next token that you are going to encounter is closing bracket. Whenever you encounter a closing bracket, retrieve top two elements from node stack. Okay, make them as child 1 and 2 respectively. Then retrieve an element on top of character stack and make it as its their parent. Have a look at this. So parent I have fetched from character stack, whereas the element on top of this stack of node stack will be child 2, and the element below the top is child 1. So what will be the structure of, so child 1 and child 2, even you can reverse it, I don't mind for that, but the only thing is you keep this funda in your mind. Okay, child 1, I'm referring to left child. Generally we run from left to right, right? Whenever we write, we go with left to right. So C1, I want to refer to left child. I'm referring to especially. C2, I'm referring to right child. Please keep this in your minds, guys. And top of the stack of or the node stack, more specifically, will be the right child. Once you pop it, the new top will be your left child. So what is the structure that you are going to get? This is the structure you are going to get. Parent, child 1 and child 2. So child 1 is sitting as the left child of the parent, whereas child 2B is sitting as the right child of the parent place. Okay. So once you have done this, now you can clearly see that addition, the addition operator over here which is acting as a parent of this tiny binary expression in near future will become a node. So transfer plus into the stack. Which stack? Node stack. Okay, transfer plus to the node stack. And the second one, as you have done all this homework because you have encountered a closing bracket, so remove one of the opening brackets from your character stack, right? Due to the occurrence of closing bracket, you have done this homework. Which homework? Picking the top element from the character stack, making it as the parent, picking top two elements from the node stack, making them as the left and right childs of the parent, right? So all this homework we have done just because we have encountered a closing bracket, right? So as the job is done, so pop the opening bracket, the pairing or the paired one, right? So from the stack, just pop it. You need not insert it anywhere. It is useless for us right now. Okay. So after whatever things I have said, this is the current scenario of character stack as well as the node stack. Have a keen look into this. So plus as plus you can see that it in the near future it is going to act as a node, right? Right now it is acting as an internal node. So I have shifted it to node stack. The job of opening bracket B and C is A and B is done. I have popped them out, right? So this is the current status where the character stack is filled with a single character which is opening bracket, and node stack is filled with a single character which is addition, right? So what is the next character? Multiplication. As it is an operator and there is no operator on top of the character stack to compare, there is no argument out there, so simply push it into the character stack. Once it is done, the next token into consideration is C. As it is an operand, simply push it on top of the node stack. As I told you, all operands will go with node stack. We know that there will be nodes. They will be converting intervals into nodes, right? So C is pushed onto the top of node stack. The next character that I'm going to encounter is minus. As it is an operator, it is supposed to get inside character stack. But what is on top of the character stack right now? So on top of this character stack is multiplication. Multiplication enjoys higher priority when compared to minus. In priority wise, in precedence. The precedence chart within arithmetic operators, division and multiplication have higher priority when compared to addition and subtraction. As multiplication is having higher priority, it will not allow subtraction to sit on its head. As it will not allow, so pop it from character stack, push it into the node stack, right? So once you do that, this is the case, let's do it. Pop the elements from the node stack, make them as the children, and pop the top element from the character stack and make it as the parent. Have a look at this one. I made multiplication as the parent. Top node stack element will be right child and the element below it will be the left child. So what will be the structure now? Have a look. Already plus is there, you know that, right? So it is the left child. It is in its position already. Now multiplication becomes, the star symbol becomes the parent. It becomes the parent, right? And C becomes the right child of multiplication. So this is the current expression tree. Okay, because of subtraction, because of the subtraction, which is having lesser precedence when compared to multiplication, we have done this, right? So in the previous slides, we have seen that we have constructed a piece of expression tree because a closing bracket encountered. Now we have done this because an operator with a lesser precedence have encountered. We have encountered, right? Right. So once it is done, that means the job of C is done and plus is also done, right? So pop C and plus from node stack. Then as the job of star or the multiplication symbol in the character stack is done, it will be popped and pushed into the node stack. Okay, so let's have a look at this picture. This is what going to happen. Let's say C, and you can see that C and plus are removed and multiplication is inserted. What is the token? That is the main point over here. The token in our hands. We have done all this job because we have encountered subtraction, which is having a lesser precedence, right? So now the line is clear as multiplication symbol is moved out of character stack. There is no operator to compare. So subtraction can come and sit on top of character stack. So it is pushed inside the character stack. Right? This is the current scenario. Right? I hope I'm clear with this explanation. The next character that we are going to encounter is E. As E is an operand, no arguments in that, simply insert it into node stack. Right? The next operator is subtraction. As the subtraction which is on top of the stack is having lesser precedence when compared to the token which is in your hands, which is multiplication, right? So you can see that on top of the stack is subtraction and the element in your hands is multiplication. The relation is less than. So on the head of a lesser precedence one, a higher precedence operator can happily sit. So stack is inserted on top of the stack, right? This is the current scenario. Then we are going to encounter F, which is again an operand. So no arguments, simply push it into node stack. Okay, so I pushed it into the node stack. This is the current scenario, right? On top of this character stack is multiplication, and on top of node stack is F, right? Now, let's check. The final character that we are going to encounter is a closing bracket. What we are supposed to do now. So make the top element, the element on top of the character stack as the parent. The same process which we have done previously, parent. The element on top of the node stack as right child. An element below it as the left child. Construct a sub-expression of the same. So where multiplication acts as the root, left child is E, whereas the right child is F. Right? This is the sub-expression binary tree that we are going to get. Very good. What is the current scenario? Once we construct this one, we have to pop. The job of E and F is done. They have done their parts, right? So pop them out of node stack. So once they are popped out, pop the top element from the character stack and push it into the node stack. So what is the scenario? E and F gets erased and this is going to get inserted into the node stack as the top element. This is the scenario. Got my point? Very good. Now you can see that the tokens in the infix expression are over. As they are over, we have to repeat the same process. What I mean is, the element on top of the character stack will become the parent. The element on top of the node stack will be the right child. An element below it will be the left child. And construct a binary tree for the same. So how it is going to look like? This is how it is going to look like, right? So when this gets hooked to the actual existing binary tree or the expression binary tree in our hands, the final structure is going to look like this, right? So the subtraction has become the parent, the multiplications have become the top has become the right child, and below that one has become the left child, right? And rest of the story, we have already constructed their children and grandchildren also. So now, if once the jobs of all these the guys is done, we can see that the job of the two multiplication operators is done. We are going to pop them from the node stack. Once we pop them into the node stack, subtraction comes and sits into the node stack. As it is the end of the string, and even you can see that on top of character stack is an opening bracket which goes on pair with the closing bracket which we encountered as the last token in our infix expression. There ends the process of converting a given infix expression into an expression tree. So for the given infix expression, the expression tree will be like this. I hope you understood this example. So basically, as I said, 2 points. First point is if you encounter open bracket or any operator, insert them into character stack. If you encounter any operand, push it into node stack. One more point. If you encounter an operator which is having higher priority than the existing element on top of the character stack, you can push it. Then the exit case or the expression construction cases will be whenever you encounter a closing bracket or an operator whose precedence is greater than, whose precedence is a or you can say whose precedence is greater than the element which is built on top of the stack, you are going to build a sub-binary expression for the same by popping top two elements from the node stack and top element from the character stack. This is how we are going to construct an expression tree from a given infix expression using two stacks, right? So I hope this explanation gives you a well understanding on what an expression tree is, how to construct an expression tree from a given infix expression, or how to write an infix expression for a given expression tree. Okay, so let's move on. Let's look at threaded binary trees. What a threaded binary tree is. It is simply a binary tree. It's a variant of a binary tree. Basically, it is meant for traversal, to make the in-order traversal faster and faster. Because if the tree structure is high, moving to the last or the leftmost element, then to its root, then to its right child. So, running from picking the addresses from the right child or the right part of any node and moving to the location becomes more tedious as well as raises the time complexity as the nodes are placed or they're scattered all over the memory. So it takes time. The time complexity increases. So to reduce that, in-order traversal is the most prominent one Just now you have seen with the in order traversal, we are going to construct expression trees, right? So in order to make the job of in order traversal easier, much more easier, threaded binary trees have come into the picture. So it facilitates the traversal in a tree in a particular order, that is specifically in order, faster, without the help of any stack or a recursion. So, what is the general process of, or if you think of a pseudocode, right? So, in order traversal of any node, how it is going to, what will be the algorithm, or right? So, the process will be recursive in order of node left, print, node data, then in order of node right. This is the basic pseudocode. It is a recursive function, right? So without recursions and to one more thing, we need to store the return addresses. As we are going for recursive function calls, we have to store the return addresses. So to store the return addresses in any functions, we use stacks, right? So moving to a stack, fetching the address on top of the stack, reaching that position, again executing is all time consuming, right? And the second part is recursion, right? So these two parts to overcome the difficulty, that is a stack and recursion, threaded binary trees have come into the picture. Okay, so threads, relations, or you can, I'll show you the pictures of it. A tiny lines will be drawn, hypothetical virtual lines will be drawn on paper, but in memory wise, addresses will be stored to navigate from left child to the node, then to right, and so on, right? So basically, these threaded binary trees are divided into two categories: single threaded and double threaded. So in single threaded, you can see that either left or right means, right? Means in order predecessor or successor will be threaded, right? Either left child from the root or the from the parent or the from an internal node, you can say, to its child, either left child will be connected or the right child. That is predecessor or successor will be connected. But in double threaded, both the left as well as the right, predecessor as well as the successor, both will be threaded. Will have hold on both. I'll show you with a picture. Have a look at this picture. So you can see that here the first node 1, is related to or hooked to or threaded to, in whatever terminology you want. Because in n number of books, n number of terminology they are going to use, just to make sure that the book they have written is totally different. But the sense, the essence of a threaded binary tree will be the same. No one can change the depth of it, right? Similarly, 1 is linked to 3. 1 being the left child of 3 is linked to 3, whereas 5, so you can see that 5 is on left of 6, right, is threaded to 6. 7 being the left child of 8 is linked to 8. 9 being the left child is linked to its parent 11. So this is single threaded. It means you can see that it is, and it is particularly this single threaded is left child threaded, predecessor threaded, pre-element is threaded, right? Coming to double threaded, both left and right childs are hooked to its parent or threaded to their parents. So you can see that 1 and 5 are siblings, right? And their parent is 3. You can see that 1 as well as 5 both are threaded to 3, right? So coming to random example, let me not take or narrate you the whole thing. Let me take the example of 11. 11's ninth left child is 9, which is On the left side is threaded to its grandparent, which is 8, and on the right side it is threaded to its parent 11. Have a look at this one, keen look. 9 on the left side is threaded to its grandparent 8, and on its right side it is threaded to its parent 11. Right, got my point? Right. So this is double threaded. So that means they are hooked to each and every node is hooked to its predecessor as well as successor, both in case of double threaded. Either predecessor or successor, either one in case of single thread. Right. So as I said, the basic application why threaded trees have come into the picture is to convert or to get the in order traversal, to convert the in order traversal, to get the in order expression of the given binary tree faster and faster. We can also say that to overcome the drawbacks which we encounter due to stacks and recursion process, right? So let me narrate you or explain you the same with a small animation. I'm going to take the same picture, single threaded binary tree, and I'm going to explain. Just have a look. So, in order traversal using threads, how to get it? As I said, I am going to do it very fast, right? So, first of all, go to the leftmost element of the given tree. So, as we know that in trees, we do not have much addresses in our hands. We have only the address of the root node. That is the address of 6. Check whether it is having any left child or not. Yes, it is having a left child 3. Now 3, is it having any left child? Yes, it is having a left child which is 1. Right? Is it having any left child? No. Right? So 1, we can say that with that small process, we can say that 1 is the leftmost element of the given tree. Right? So make it as the output, the first character in the output, or the first character in the in order traversal. Then where 1 is heading to? 1 is heading to 3, right? So now as you have traversed to 3, so the next character is 3, right? Now you can see that once you are at 3, so as you have traversed towards the left, from left you have come to the root, right? So from 1 you have come to 3. Then in which direction you are going to move? That is the right child, right? That is the only go. Left, passing towards the left is done. Parent is done. Now we have to run towards the right. What is the element on the right? 5. So next character in infix expression will be 5, right? So now to which element 5 is hooked to? 5 is threaded to 6, right? So as 5 is not having any left or right child, it is directly threaded to the root node 6. The next character that we are going to present in the infix expression or in order traversal is 6, right? So with this note, I can say that the left subtree of 6, passing of it is over. We have traveled through all the nodes in the left subtree of 6. Even touching the root node, which is 6, is also done. We are left with the right subtree of 6. So come, let's go in this direction. What is the element that you are going to encounter? 8, right? So once you encounter 8, right? To which element the left, is 8 having any left element? Yes, it is having a left element. Go towards the left element. You will reach 7. Is 7 having any left element? As I said, we need to go to the leftmost element. So as 7 is not having any left element, so 7 becomes the leftmost element of right subtree of 6. Understand my lines, guys? 7 is the leftmost element of right subtree of 6, right? So as 7 is the leftmost one, I'm going to introduce it as the next character in order traversal. Once 7, we reach 7, right? To which character, to which node it will point to, or it is threaded to? It is threaded to its root, which is 8. So 8 is the next character that I am going to traverse. That is 8. Once this is done, we can see that the left subtree of 8 is passed or traversed. Now it is the right subtree which needs traversal, right? So the right subtree of 8 is headed by 11. Okay, then is it having any left child? As I said repeatedly, you need to go with the leftmost child. So yes, 11 is having a left child, which is 9. Is 9 having any left child? No. So 9, you can say that 9 is the leftmost child of right subtree of 8. So what is the right subtree of 8? This one. And the leftmost element of this right subtree is 9. So mark this as entry in your in order traversal. Great. Once 9 is entered, now our control is at 9. To which element it is been threaded to, which is 11. So mark an entry of 11 into the in order traversal. 11 is entered. Now we can see that the left subtree of 11 is passed. Even the element 11 is touched. Now we have to go in the right direction of 11. And the right direction of 11 is headed by 13, right? As it is headed by 13, now we have a look. We need to go in the leftmost direction. Is 13 having any left child? No. As it is not having any left child, I am going to go with 13 as the next entry, right? So, as we can see that there is no left child for 13, not even any right child for 13. Now I can say that I have finished my job of converting a binary expression, that is the expression tree, into an in order traversal, a list of in order traversal elements as I reach the rightmost element. I've started with the leftmost element, which is 1, and I ended at the rightmost element, which is 13, right? So this is the final in order traversal using threads. Yes, if you want to recheck, you can check. Remove the threads which I have given over here, the links between 1, 3, 5, 6, 7, 8, and 9 and 11. Do normal in order traversal of the given binary tree. You'll get the same result. You can do the reverse engineering job also. Most welcome for that. Yes, I hope you understood this one. Right? In today's session, or in this session, we have learned about two kinds of trees. One is expression tree, and the other is threaded binary tree. Okay, so first of all, expression tree is a tree in which binary expressions are stored for easy evaluation. For that, for any fixed expression, given expression, to convert it into a expression tree, fixed expression to expression tree, we need two stacks. One is character stack, the other is node stack. Using the primary algorithm of the same, we can construct it easily, and we can observe that expression tree is free from brackets. Any kind of bracket, they just act as barriers. They act as barriers between the sub expressions. For example, if I take 4 plus 5 multiplied by 5 again divided by 3 plus 2. So here 3 plus 2. is an operation. If I remove this one, 4 plus 5 into 5 by 3 plus 2, what is the result of these two expressions? Guys, you calculate and tell me. So 4 plus 5. First of all, if you use brackets, this will turn into 9 into 5 by 5. Or else, it will calculate 25 first, then 25 by 3, then this will be the result. Total, completely other side of the coin. So to impose priority or to give priority to sub expressions, we use brackets, right? So when we convert and keeping in mind the priorities which these brackets provide, expression trees are converted, which gives you which provides an easier way for our arithmetic logic unit to evaluate an expression, right? The other side of the coin, we have learned about threaded binary trees. These threaded binary trees help us to get the in-order traversal faster, as they do not need any stack or recursion, which leads wastage of time complexity, which raise time complexity, recursions raise time complexity. So to avoid that, threads have come into the picture. And two kinds of threads we have seen: single thread and a double thread. In single thread, there will be relation between the left child to the parent or to the right child and the parent. In double binary threaded trees, the parent will be hooked to or threaded to the left as well as the right child also. Right? This was the gist of the things that we have covered in this session. I hope this session was useful. Please do follow, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.